Alrighty, let us talk about things. Okay, so we have a new pointing device. All right, so today we're going to talk about random walks, and that's going to lead into talking about mechanisms for power law size distributions, which you are apprised of now, right? Because I put those lectures up, and I will presume you have watched them. There are counts on the YouTube thing, so I have some sense of it. But so that's the game, though, right? So I don't know who's done what, but let me see. So here you go, right? That's the piece of information for the missing lecture on Tuesday, right? So here are the two lectures to look at. Actually, if you click on these, it should work. YouTube keeps changing. What? Didn't work? So, look at this, though. Like, see? See that? Yeah, moving across. It works on my computer. Wow. That's really weird. I put question mark t equals thing. I worked on this in my conference. So, all right, I don't know. You used to be able to put and. Whatever, this is madness. Flash, it's still Flash. Horrible. Okay, 1.21 gigawatts, I should say. So apparently no one on the set of Back to the Future knew how to pronounce that word. So that's what happened. Or the 1.21 thing escaped them as well. So, but anyway, it's baked into law. Anyway, so that's what we're up for on Friday, and these are the pieces that help you. All right, so I'm going to presume that is in your head. I might talk about it very briefly. Just quickly about where we're going from here. We have made it through to, right, this piece has been done, so we're going to talk about this today. So I'm going to call it mechanisms to get to power law size distributions part 1 and then part 2. This will be about randomness. This will be about another kind of but random growing mechanisms, incredibly important sort of mechanism, and an optimization mechanism, right? So that's going to come back. You know, to what extent do engineering and natural systems produce things that are results of randomness, you maybe get them for free, versus ones that are optimized in some way. Big system stories. Benford's law is about why you shouldn't cheat on your tax, unless you don't have to release things, I suppose. Anyway, so, and then there's a piece here on fundamentals that I'll get back to, includes things like statistical mechanics and just sort of some older pieces there, and that just sets the stage. I used to kind of have that at the front, but I want to get you into some assignments earlier. That's the plan. Here's our emblem of robust yet fragile, right? So a lot of systems, they're just around for a long time and then they go pop. And that's a good example, although no one learned from that one. A lot of jobs lost there, actually. So, and there are t-shirts, depends whose side you're on. Okay, two sides. Okay, so robustness and fragility, right? And there's a scaling story there, and somehow that is connected to where you will put Starbucks in hospitals. That's a big piece we're actually kind of working on now to try and make that more clear. But this is something that grew out, some of these pieces grew out of my complex networks course, and I've shuffled things around. This one I've just like extracted completely, so it's like episode 4. There are a couple of pieces that come before it. But this is about optimal networks. How do you lay things down so you can supply, whatever it is, it might be supplying coffee, caffeine, very important, or help, in service of, say, public schools or hospitals. How do you lay those things out? And then we get, eventually, there's some more stuff here, then we get to networks, and that's a gigantic story that has gone on for the last 20 years. Still going, there's so much to think about, of course, but I'll tell you about some really classic pieces here, and then we get to spreading, how things spread on systems. All right, then there's more stuff, but that's just to give you a sense of where we're going, and so I can remind myself. All right, so these are the pieces that I wanted you to catch up on. All right, for some reason the things didn't work, and you had to find your way in there. Anyway, so this is right. I didn't want you to watch all of that. Good. Anyway, it tells you what to do at the start. And here, this is the, that's the same one. And then we wanted this. Yes, right. Oh, Clauset. I just saw him the other day. Very good. Okay. Some other things. So we're going to get to, I'll talk about ties, actually. This is from my college back in Australia, Trinity College. It's like the English system. You have Melbourne University and all these colleges who hate each other and, compete in various ridiculous rowing races and so on, except it's really hot. Doesn't make any sense. Right, I mean, you go to dinner with the gowns on and the oak tables and someone carves at one end. It's all this madness. Grace is said in Latin, except it's 110 degrees and you're in Australia. And yeah. Anyway, slowly evolving. Okay, we'll get to that. For some reason, that has something to do with random walks, actually, which is odd. Okay, let's put this away. All right. Okay, this is the piece that I want you to get into your heads that I didn't, I wasn't here for, but a previous version of me was, so that has been supplied. Zipf's law, right? You should understand this Zipf's law story and how it works with size frequency distributions. Very happy to talk about that in office hours, which will be, again, today, usual thing, from, let me get it right, 1:15 to 2:30, right? Yeah. So I'll be there for that one instead of on an aeroplane. Okay. Good. All right. Okay, so there was a piece here that I figured out while I was away. So this is what, so we did that little questionnaire thing, right? And this is for the quintiles of wealth, and it's really for about the wealth in the US in 2011, so it's increasingly inaccurate, much like the Hitchhiker's Guide to the Trilogy, the increasingly inaccurately named trilogy with 5 books. So this was the actual distribution, right? So the top 20% had, what would we end up with? It was close to 85, I think it was, yeah. Right, this is on a funny scale, I suppose. This is truncated. Oh, it's the 100, it should be 100 at the end, but there's a reason it isn't, is because not everyone got everything to add up to 100. Okay, so no names, but just, and numbers had to get smaller, okay, so that was the other little piece there. But this one didn't quite make it all the way out. Someone missed it. 20, I did my best to read your writing. I was sure it was a 60 instead of an 80. Anyway, you did pretty well as a collective, so that was pretty good. So you can see this is spread. People thought it was like this is a king and everyone else situation, right? I mean, maybe we're going there. I mean, it's true the Gini coefficient, which is a measure of inequality, has been going up for a long time. So this is a prediction of the future. This just doesn't exist, right? This is some fantastical land, and this is what you guys collectively, or thought would be good. So you're a bunch of raving socialists, which, as we saw in that paper, was true for everyone. People who voted for Bush or Kerry, right, or were wealthy, or not as wealthy. Then they generally agreed. Actually, again, some issues with the little adding up bits. Missed it by that much. Also, I think Maxwell Smart. I know. Get Smart? No, this is a long time ago, but that's right. Okay. Okay, Inspector Gadget. All right, so this kind of, the wheels came off here a little bit because the idea was, the top quintile, because you're ordering people from wealthiest to least wealth, right? So the top quintile has to have 20 or more % of the wealth. So I think this was the Robin Hood thing, which is like, given this situation, that's where they should go. That's kind of how I interpret it. This is what you think should happen tomorrow, yeah. So you're some revolutionaries in the team. Okay, but this is, not the truth. Okay, so, and if you look at the past, because I've done this for a few years, so this is 2014. Somehow I didn't get the paper back in 2015, so I just missed it. But, sort of a similar story, right? Also some issues with the adding up. That's it's always going to be a glitch. Everyone has trouble with that. Also with there's a little bit of that. No, that is bigger than that. Okay, so that's been true as well. But I think if you go back, you see these ones. These estimates are not. You guys are more skewed, right? I mean, I think as in these last 4 years, people's sense of things has actually started to become more aligned with reality. Usually the students I've had in the past who are economists, they're right there. And they're more extreme than that usually as well. They know reality pretty well and they want it to be like that. Okay. There is a paper actually on the people who think most like rational economists are economists. It's an interesting paper. It's really true, right? You have to be trained. It's not human.
I was wondering if you ever calculated what the average of our is compared to, is that on any of these?
Yeah, so the top bit is, I guess I didn't do that, right?
It'd be interesting to
No, I did do that. This is your average. Yeah.
Oh, okay.
Yeah, sorry, this is your average. Yeah. I don't have the original one to compare. That's, yeah. So, this is insane, right? This is, Scandinavia doesn't have this.
And then reality is the top one.
So the reality one is reality would be back. I think it was just after this, right? Sorry, yeah, I could include that near the end. That was all those stress.
Okay.
That's why, I got myself confused, really. Okay, so yeah. So we can ignore these ones. I mean, you could compare yourself to what people thought at the time. Right, so there's a fair blob here, the top 10%. This is the bottom 40% quintile, so 10% there. I could include that. And that's not the case here at all, right? Yeah. So you're getting better at it. But this is sort of maintaining this insane, All right, so you should start a revolution. Okay, but it is funny because if you ask people right out, it sort of forces them outside of their context and so on, they answer like this. Peter?
So what are the bars that go past 100 or don't go to 100?
Oh yeah, so this is I was just faithfully putting in the numbers people recorded, and not all of them added up. And not all of them decreased. So I wasn't going to adjust them, I'm just being, yeah.
So it's interesting that both of those sum to the same amount.
I didn't quite say this, but I wanted you to absolutely not look at what anyone else had done. I hope that was the case. I wanted you to write down what you'd done, and faithfully copy it on, because I didn't want any, which sort of what you just said worries me. But you're right, they're the same up until one. Yeah, but this is also, these people aren't adjacent, right, in the class. It's just random. Yeah, I've sorted them according to the first estimate. All right, so very good. That was fun. Okay, did anyone get 13/27ths for the, yeah? That takes a little thinking. Yeah, all right. Not obvious though, right? You don't just go 13/27.
Have you ever asked the question like the other way, but like ask how much, rather than asking how much wealth you think each poor child should have?
Yeah.
Ask 20% of the wealth goes here, 20% here, how much of the population?
Oh yeah. So you can do it that way as well. And in fact, we have a question later on which gets at that, because there's things like you'll hear and there's the 99%, the 1% idea, which doesn't tell you how much wealth they have, right? So it's just left out. But then there are things like the 80-20 rule. Like people will sort of invoke that, even say for work, or 90-10, 10% of the work, the last 10% of the work takes 90% of the time, or something like that. There's a touch of this idea, because it's a very skewed distribution, and it's just really getting a couple of points out of it. So we can get to that with sort of a question about it. Like, how do those two things compare? It'll be on a continuous slider, right? So which fraction, it'll be around that, right? So if 90% of the people have how much wealth? And then, depending on the slope of this power law size distribution, how does that change? And what can you get? Can you achieve all these things? So if 80% has 20% of the wealth, which is sort of a nice little story, what does that mean for 70%? What does that mean 70-30? And it doesn't, right? It's not as simple as that. You're just waving your pen around. Okay. Totally endorse that. All right, so, okay, good. That was fun. I thought that was fun. Okay, Pratchett is doing well. I could show you Pratchett videos all day, but we won't do that. Okay, so this is where we are. All right, we're going to look at random walks. What's that?
Silly.
Yes, which could be construed as silly walks. So this is very small reference here. This is John Cleese's hat in that scene from Monty Python. John Cleese is coming here, actually. They'll be at the Flynn. There's just John Cleese on a stage being John Cleese, which is awesome, and I can't wait. Okay, so the Snormals, right? So there's this idea of getting to these very boring sorts of things, but these ones are where we'll go afterwards, right? So we're going to go to two of these places, but even the Snormals have some interesting aspects about them. So this is a very general thing about getting to structure, right? So we have this universe boiling away, and eventually we've got us and platypuses, which is pretty weird. But a lot of stuff that's going along, and I'm just touching on this, is that randomness can give rise to structure, right? So there are lots of things about ratchets, for example. Once something starts, and it can kind of keep building in a certain way instead of just destroying itself and falling apart. Okay, origins of life, big story. People worry about this a lot. Not really solved yet, but let's just talk about random walks as a kind of a nice mathematical example that has some real physical and practical aspects as well. So the essential random walk, maybe it's the liquids. Oh, I decided the other day I have to like your car keys, right? In this. So one spatial dimension, right? So we're just going to have a line. So imagine, all right, we'll use these tiles here, right? There's sort of a tile here. So it's going to be very simple. You're going to have someone who is very erratic in their decision making, possibly because they're inebriated, and they will take one step at they're very faithful to this part though, I keep saying faithful. Every tick of the clock, they will move one way or the other, right? And it's just going to be in one dimension. So there's time and one spatial dimension, and they just randomly move from side to side, right? So this is going to trace out a random walk. And there are lots of questions about this, right? I mean, the stock market, for example, has a lot of random-like behavior, very much. Black-Scholes equation is all about that. But now and then it doesn't, and that's when you lose all your money. Or if you're very, very sneaky and guess the other thing, you win. Here's a really basic question, though. So say this is time 0. Okay, sorry. Time 0, and we'll come back to this one. And every tick of the clock, I have to move. I flip a coin, I randomly move one side or the other, right? That's it. And it's like heads, you go this way, tails, you go this way. So, heads, I go this way, tails, I go back, so I'm back where I started. So this becomes this problem of first return. What's the probability that after, and it can't be an odd number of time steps, right? So an odd number of time steps, you'll always be on an odd position. This is 0, 2, 4, 6. That's where you'll be after an even number. So what's the probability after 2n ticks of the clock, you'll be back at 0? Or you will return for the first time. Okay.
This assumes that each step is equidistant.
Right. So we do the simplest thing, which is there's a clock, and then equidistant. And then you can vary all those things, right? So you can draw from a distribution for distance. You can draw for a distribution for the time for the movement. And if those distances have a skewed distribution, which is sort of what we'll call Pliplo, power law in, power law out, that then you can get these weird things called Levy flights, actually. Yeah. Okay. But we're going to keep it really simple. So time and space are discrete. We have this person who's drunk, and I'm not advocating this as a behavior. And then plus or minus 1, probably a half. You just move. And so we'll call this little variable epsilon of t, right? That's it. Very simple. So tons of stuff come out of just this really simple thing, and it connects to all sorts of math and other kinds of, as I said, physical pieces. Sorry about that. What is happening with my terrible... Wow, that was weird. Okay, so there's a few random walks, and this is 10,000 time steps. These are fun things. They're very easy to simulate using whatever code you like. I mean, we've spent a long time figuring out how to do random number generators, and people do all sorts of crazy things, to get that to work really well. But we're pretty good at that now. So here are just some examples. These are, if you like, random examples. They're not chosen terribly specifically. But if you think about this problem of first return, well, this one came back pretty early on, then got away for a while, and then there's this huge amount of time where, so you've got more heads than tails, right? So if you're playing a game and you're winning money, if you're on this side, it's all good. Eventually this one came back, right? Went like this. But they start to give structures that you think, well, these are sort of, we see lots of things like this that are kind of rough-edged and so on. And then I'll mention this briefly at the end, but this is a kind of fractal, and there are other fractal shapes where the jumps are a little stronger or they're a little smoother, and in fact there's a whole spectrum of these sorts of shapes that you can build. Early on in the 80s, people got very excited about fractals, and they started to build landscapes, quite reasonable looking landscapes with these fractal landscape generators. All right, so we're going to do a little bit of math, simple things. So after t time steps, we're just, the position we're at, right, along this line here is just going to be the sum of these little displacements, right? So they can either be plus or minus 1, and we're going to flip our coin to realize them. And then we'll just do some simple statistical things, right? So the average position, right, where we expect to be after t time steps. Well, it's a sum. It's the average of the sum, and it's the sum of the average, right? So averages, and the averages are 0, right? So Of course, you never actually move zero. You never have zero displacement from one step, right? So either this way or this way. On average, you move zero. Okay, so that adds up. So all of these are zero, so this adds up to zero. Come on. Well, that doesn't work. All right, so let me move this thing. What's happening? Oh, batteries, maybe. That thing, it does for your car keys. Yeah, you put it on your mouth for your car keys or here. Yeah. Or is it like your skull makes it bounce in the right, yeah. Weird but true. Okay, so anytime you'd expect, on average you expect them to have not gone anywhere, right, from this simple thing. And this is no good for an odd number of steps. But you'd think the chance of our, the coming back must diminish. Fair enough. Okay, well, let's look at this. So another piece is the variance. Okay, so the variance, simple statistics story here again. So the variance of this variable xt, which is the sum of all of these little pieces, plus or minus 1. So variances have the same rule, they sum. I wish I could get this to work. Is it that thing? Sorry. Let me try to break some things. Okay. All right. So the variance of each of these, so that's pretty simple, right? So it's variance of a random variable. So we're looking for the sum of pi, in this, let's say our variable is x. So the variance, and it has probably p, it's a discrete variable, so the variance equals this guy, right? So it's the expected value of x squared, sorry, let me put this, minus mu squared. So this is the average, the mean of x, this variable x, often we write as mu. I'll tend to use this kind of notation, which is sort of physics one, these angular brackets. So it's the average of this, the displacement from the mean squared. And the displacement from the mean for these things is just 1, right? Because the mean is 0, so it could be either plus or minus 1. And plus or minus 1 squared is 1. Right? So we have this piece here. We have really the variance for each, the variance of this epsilon character is a half, right? That's probability of, say, a minus 1 squared. Right? It's really minus 1 minus 0 squared plus a half plus 1 minus 0 squared, right? So this is the mean. This is moving plus 1. It's got a probability of a half. So a half plus a half is 1. Okay, basically. So sum rule is very nice, and that helps us. That's a good thing for using the variance, which is a bit odd in some ways, but it's a reason it's there. So the sum of 1 from I equals 1 to t, right? We're just summing these up, is just t, right? We've got 1 plus 1 plus 1 plus 1. T times. So that's the variance. So the standard deviation, which is the square root of that thing, is t to the half. All right, so now we're getting some idea. So on average, it's you expect the character to be here, but as time goes along, the standard deviation of the distribution of where it could be is growing like t to the half, which is slower than time, right? But it's growing. So you expect to see some spreading. So if you had a lot of, and here's the thing to think about, you have a lot of walkers, right? So you put down 1 billion walkers and let them all go at once. Some will pile back here, slowly be sloshing around, but you'll see some further out, and you start to see, in fact, a Gaussian distribution emerge slowly, which is a beautiful thing. So it's this is an important kind of scale. We've had a big section on scaling. This is a basic kind of scaling, simply coming out of random walks, which is nice, right? All right, so that is one thing. And I don't think this is going to work anymore, yeah. Suddenly this just changed. All right, okay. So I'll show you this a little bit if I can get it to.
So here's a frame.
So I don't really want to, basically this is a a Golden board or a quincunx. There's various words for this, or names of this thing. It's actually a machine. I think this is, where is this again? Let me expand it. And I'll just jump through. I don't know, I had these little games as a kid, right? So the idea here, right, is they're dropping all these balls down, and let me get the right thing. So yeah, you've got this big structure up here. The balls are just coming in through that top hopper, and then they've got a 50-50 chance, right? All the time, if it's well designed. And so it's creating exactly, they're making all these little walkers, basically. And in a sense, the number of steps they have is then, right, is going to be the depth of that, or the number of rows in that filtering structure up here, which is the quincunx. All the balls are coming back up. Don't worry about those. That's the number of time steps. So this is going to be a distribution after whatever it is, say 15 steps. And you see it starts to fill in this Gaussian. All right, pretty cool. Totally awesome. All right. And if it was, right, so if this thing was, deeper, then you'd have a more, if this triangular lattice here of little rods was twice as long, then you'd have, this would be wider, but it wouldn't grow, it wouldn't be twice as far, right? Because this typical width of this thing is growing as the depth of that to the power of a half. So it's getting wider, but slowly. So this is diffusion. I mean, this is a ubiquitous aspect of physical reality, right? Things diffuse, right? If you think about landscapes, they tend, like Australia, they just flatten out. If nothing is pushing things up, flatter and flatter and flatter, right? Through random behavior. Okay.
So these measurements of the distribution are true regardless of the number of steps. Therefore, arbitrary number.
These pieces here, yeah, these are just about, so these are just about epsilon, just about each step.
Oh.
Right, and then what we talked about, so what we have is, this is just a general statement. This is variant for epsilon, and our thing here is we have x of t is the sum of these epsilon i's, right? Right, each one of these things could be realized as a plus or minus 1, and we're just going to flip coins and then add them up. Yeah.
And so then you could, from there, expand those.
The last one in $10,000. Now he gets that over.
Right, Price is Right has
Gets that one
Plinko.
over.
It has one of these things
That
on
has
it,
never
and you win lots of money if you get it in the right
incidentally.
spot.
That was an historic moment on The Price is Right.
Yeah, which I'm sure he's bored out of his mind, but yeah, that one didn't go into the right spot. Great moments in Plinko. So does that?
Yeah, I think so.
Right? Yep, Laura.
So for that like distribution curve, is that like time on the bottom?
So the in the physical one?
Yeah.
Yeah. Okay, well let me show you, I'm going to just jump to, I'll come back to this, but I want to show you a picture. Yeah, here. So this is time here, right? So time is going this way, and then this is x, right? So this is this position on the floor here, right? This is the position on the floor. So time is just mapping out, but you can imagine that the walker is just going, like in a physical space, is actually just going down, back and forth on this axis, right? And we make it a two-dimensional thing by introducing time. And so here's a walk, right? So an example one. And then if you had many of them, you get these distributions at these particular time steps. Okay, and each one, I mean, this is discrete, right? So they're just little histograms. It's always going to be true, and they go from even to odd, right? There's nothing in an odd bin after an even number of time steps and vice versa. But this distribution gets wider, and its characteristic width grows like this. This is sort of a 95% confidence interval for the.
So it's mostly that like whoever's gonna get starting
Say it again.
based on like the height of the sideways curve.
Yep.
Like it's most likely that they're going to be
In the middle. Yeah, exactly. Right. So you expect them here, and this decays like e to the minus x squared. It's a Gaussian. So that really truncates pretty quickly, and it's e to the minus x squared over 2t because It's 2 sigma squared in that thing. We'll come back to it. You get to prove, but it's 2 sigma squared is the famous e to the minus x squared over 2 sigma squared. That's the Gaussian structure. Yeah, and sigma in this case is root t. So it's going to be x squared over 2t. That x squared over t is really this beautiful diffusion structure. Yeah. All right, let's sort this out. Okay, so so there are 2 things, right? So I showed you that Gaussian distribution. As you said, there are a lot that end up at the say the mode thing is 0, right? Is the center. But there are all these different specific walks that get there. And the probability that a walk traces a specific route, you started here, and it probably traces a specific route, is actually 1 over 2 root t, right? 2 to the power of t, because there are t time steps, and there's a half a chance each time that they stay on that track. So each one is special, right? It's just that when we say we only care about where they end up, then we get this kind of collapse and we say, oh, there's a whole bunch of them that end up there. But each specific one, if you say, what's the probability that this actual trajectory occurs, then we know exactly what it is. It's a half to the power of t, because at each time it has to traverse, it has to keep going in that direction. And we're going to lose a half of them every time. So that's one thing, but we're more interested in how random walks end up in the same place. And so we're going to talk about that with this quantity. This is something you'll use a little bit. So it's going to be, this is the number of walks that start at position I, right? So I is 0, 1, 2, or -1, -2, right? So it's an integer. Ends up at j after t time steps. Right, basic thing. So we want to be able to compute that. So we're going to start at x equals I, end at x equals j after t time steps. So to do that, our walk has to displace in those t steps by j minus I, right? So if you like, you can say I plus j minus I equals j, right? So if this is 5 and we're trying to get to 9, 9 minus 5 is 4. We need to get plus 4. And if, maybe we have 300 time steps. After all those time steps, we have to have just got exactly to plus 4. Right? So to come back to 0, we'd have 0 and 0 here. Okay, so that's a problem to sort out for you guys. You can do it. This is a binomial, right? This is t, and then we've got the t here, and then this is the displacement divided by 2, right? So this is a thing you can figure out. I'm going to leave that for the assignment, but it turns out to be it's obviously a counting problem, and counting problems often end up with binomials, right? So binomials are a very important piece here, right? So this is t, choose this blob. How many ways are there of choosing this many things from t things is the way to think about that. Okay? So it's a little question, and that's just a start, because then we can play around with it. So how does this thing behave for large x, right? So this actually, I'm sorry, I don't know what to do with this. Come on. This really is our if we put 0 here, and we say this is kind of x, right? This has to tend towards a Gaussian. Or we're going to claim it tends towards a Gaussian. This binomial will, if we do the right things, for large t and large displacements, this should start to look like, well, actually not too large, but certain kinds of displacements, we have to be careful with it, we'll get a Gaussian coming out. As a continuum approximation, it's a discrete thing. Very nice. So there's some sneaky stuff to do there. Okay. All right. So we're going to do even time because of this issue of, this discrete thing. There's no way we can come back to 0 unless we're on an even one. So we'll just restrict that to help, clean things up. So after 2n time steps, we could be at position 0, plus or minus 2, plus or minus 4. And the furthest we could be away is 2n, right? 2n that way or 2n that way, if we'd gone. So that means 2n heads in a row or 2n tails in a row. And so they become increasingly unlikely, right? So there's, as n increases, and that means there's only one way to get to 2n, right? You have to have all heads, or whatever it is, or all tails. But there starts to be increasingly more ways to get to 0 and to plus or minus 2, plus or minus 4. Okay, so we know it's going to be even, so we'll just say, let's say it's 2k, right? Just to kind of, this is just algebraic hygiene. So we don't mess ourselves up too much. Well, we will, but not too bad. Okay, so we actually have, the expression that you figure out on the previous page. If we put in I equals 0, 2k, and 2n, then it boils down to this. I'm talking about the probability here. The number is exactly equal to this, but we want to get the probability. So there's a piece in here about normalizing it properly. But let's think about this. This should make sense. So we've got 2n time steps. And what's this binomial? It is, I guess I should just write it on the, okay, I'll do it here. Yeah, so it's 2n. We can just see that this makes sense. N plus k, choose this, right? And so the definition of this thing, right, is 2n factorial over n plus k factorial, and then 2n minus n plus k factorial, right? So it's always the blob on top. Sorry. Oh, that's what it did. Yep. The blob on top, and then the blob on the bottom is here, and then we have, it's a symmetric structure, right? Right, because this also equals 2n n minus k factorial, right? We can either choose n plus k things from 2n or n minus k things, because these two numbers add together, right? So n minus k plus n plus k, that's 2n, right? These cancel, and we get 2n. You can choose 3 things from 7 things or 4 things from 7 things, because they are the same activity. All right, so that's exactly what this blob is. I guess I jumped a little bit. This is n plus k factorial here, and 2n minus n plus k is n minus k factorial, right? So the symmetry is there. Okay, so what this is saying, you've got 2n time steps, and we're trying to get to 2k. So this would be, we could think of this as our plus ones. So this is our number of plus ones, and this is our number of minus ones. Right, so if we say we're choosing, we have 20 time steps, and this is 13, this will be 7, right? So that's how we get to 6, because we'll have 13 steps in plus 1, and we'll have 7 steps going the other way. 13 minus 7 is 6. Okay. Right, if k was 0, we'd have n plus 1s and n minus 1s, and that means we've come back to 0. That's the case where we come back to 0. Okay, so it makes sense. You get it from the formula we had on the previous page, but there's also, it's clear. Okay, so then there's an activity to show that this blob, this rather, it's got some n's and k's, it's not too bad, actually turns into this thing. So we can work through that, but that's an assignment question. It's a good thing to work through. It's a good thing to come to office hours and work with your teammates. I want to remind you that you should be part of a team by this point. I mean, you don't have to be, but I really hope that's the case. But somehow, magically, you get good things out. Pi's appear. Pi's always appear, right? Yeah. But you get this, and this is the correct normalization for the Gaussian, right? It's a probability distribution. There's some slight tricks in that. There's one little trick in that because of the way this is working, it's either 0, 2, 4, 6, 8, right? There's nothing at 1, plus or minus 1, plus or minus 3. So there's a little correction for that, a factor of 2, essentially. So we started with a coin flip thing, and we get this out, right? We get a Gaussian out. There's no Gaussian inside the little coin flips, right? This is just a very nice emergent story. And more generally, right, the central limit theorem, this is just one way, this is just one sort of clear path getting to the Gaussian. The bigger, more powerful story is if you have, if you're summing up variables that come from distributions with finite variance, right? Nothing is too explosive. You're sampling, there could be exponential distributions, there could be all sorts of things. There could be a mixture, right? then you'll get the central limit theorem, the Gaussian appearing, right? So this is a really profound story. It's why the Gaussian appears so much in the real world. You're summing up just little bits of whatever. Doesn't really matter. As long as those little whatevers don't have explosions inside them, right? None of them can be too big. Basically the story. Okay, so that's very nutritious. There is, for the people who who really want to get into probability, stable distributions is sort of the more general story here. And that's, so the Gaussian is very special because it is this sum of things, and it also has this nice property. If you add two variables that are Gaussian distributed, you get another thing that is Gaussian distributed, right? The variances add, the means add, the variances add. There's a continuous set of them where the index goes from 0 to 2, I think it is. And there's an inverse Gaussian distribution. There's the Laplace distribution. So and all of these other ones, though, have power law tails. So they're quite different, right? They're a different set of beasts. I just want to point that out. Okay. Good. And they're called stable because if you take two variables that are distributed by these distributions and add them together, you get the same distribution back. Increased variance, but you get the same form. Okay. So how we doing with this? Yeah.
So that's this dashed line you have. That's the confidence interval, and then.
Yeah, this is showing this the typical width.
And
Yeah.
T would be the max.
Right. Exactly. So there is in fact a straight minus T and plus T because this is a discrete story, right? That there really is this. Once you get out here, there really is this kind of hard edge to it. It doesn't really ever decay as e to the minus x squared perfectly. In the limit, though, it does, right? Yeah. Is that okay? I don't know if this is really true, but even things like steps that have been around for a long time, you can start to see like Gaussians inverted in them because people walk down it. Like old stone places, yeah. But that could have a reinforcing thing, so it's probably going to deviate from a Gaussian. But you see stuff like that. Okay, shout out to the Princess Bride at the top. Okay, so this is the random, and this is Princess Bride. Random road through the forgettable forest, right? So this is a random walk, and it's exactly that picture just playing around, right? So we have this nice random walk, we have some nice shaped objects, right? T to the half T. So it's not doing anything crazy. Everything is normal and well behaved. That's a joke for it. Snormals, okay. So there's some weird things about them, and I've talked about this idea of return, so let's get to that a little bit. So this C thing is probably that by time step T, a random walk has crossed the origin R times, right? So you start off, let it go, and you let all of these little ball bearings go, or whatever they are, people who have had too much to drink, and then you count up how many of them have come back R times to their origin. And normalize it and get a probability. Coin flip game, right? So and then you start to think about, well, if you're behind early on, and I showed you a couple of examples, what are the chances you make a comeback? Right? So if you're behind by 10 coin flips, what should you do? Should you just hang in there because you know that, on average, you should be equal, right? At any point in time, that was the first thing we did. Any point in time, the average score differential should be 0, right? You should go back to 0. So, that sounds pretty good. So this is weird. The most likely number of lead changes is 0 for these 10,000 time steps, right? So there are 0 times lead changes is actually 0 changes is greater than probably that there is 1, 2. These things also add up, of course, to be bigger than this one. But that's pretty weird. It's pretty weird because you think, especially at the start, there's half a chance that you go straight back to where you were, right? And then this is the very strange thing. So the expected time between tied scores, right? So the game is tied. This is a terrible game. But it's true, actually, there's a lot of randomness in games, right? So analyses of NBA, of NFL, hockey. We have a paper on this. Aaron Clauset I mentioned before, has some work on this too, and there's work going back into the past. A lot of it looks pretty much random, actually, which is disappointing. But we put stories on top, right? So, so the expected time between tie scores is very weird. It's infinity, right? So here's a tied score, if you like, right? I represent the difference between these two teams, and team A gets ahead, so they're winning, right? I mean, it's still, I'll go back with a 50-50 chance. But if you start to walk over here the next time, a little bit of a less of a chance, and the average time that it will take to get back, the average time is actually infinity. It's very strange. I mean, there's a probability you return after 2 time steps, and probably you return after 4 and 6 and 8, but it decays in such a way that the expected time, right? Because some of them will come back after 2 time steps, some will come back after 4, some will come back for the first time after 10 million time steps, right? And if you combine all of those, on average, the time is infinity. So you should not play gambling games at all. If you really want to get into this stuff, Feller is the beautiful, beautiful work on this. There's 2 volumes. Okay, so let's do one. That was very weird. I'm going to do this. It's weird to wear ties at school. And this is crazy. Okay, so look at this. So this is a paper in Nature. Well done. I mean, 1999. They turned tying ties into a random walk problem. So here's you're starting here, right? This is the starting situation. And then you either can go left, like into the person, or out of the person, or into the shirt, out of the shirt. So that's what the little, if you're from physics, you'll sort of, right? That's an arrowhead, and that's the back of the arrow. Or you could go right, or you could come through the center. And you come through the center like this, like this. This is very confusing to think of. This is set up so it looks like what it would look like in the mirror. So, yeah. Anyway, so what they did, this paper is unbelievable. They just imagined all these little random walks that end with, they're actually ties, right? Because you have to come out through the center at the end. And then computed a bunch of things for them, like balance, like how many times you go left and right. And then a winding number, which is, do you go, like if you start to go too much like this, that's not going to work, right? So if you wind too far one way, it's going to look silly. I mean, it always looks silly, but so you want the kind of winding to be balanced out. So they have a bunch of measures for this.
So this is the inebriated person we want to tie.
What is it?
This is the inebriated person.
Yeah, right. And so, so they just let it go. And then some of those inebriated people will produce a tie that's not bad, actually, right? So these are the ones that turned out to be known. This is the Windsor, which I was told by the senior boys to use because that was the cool one. It's somewhat complicated. I have to say, when I read this paper, though, I realized I'd been messing it up for a bunch of years, which was really weird. I'm like, my God, this stupid paper. Anyway, so you have a bunch of things in here. Let's see. So this is the number of moves, which is H, right? So there's sort of a raw complexity. This is the number of center moves, so how many times you come back through the center. So that's an important kind of ratio. This is the number of possible ties that have that many moves and that many center pieces, right? So this is a little, this is like what we were talking about for our random walk, right? We could count how many random walks ended up at 3 steps away after 14 time steps. That's what this is doing here. I mean, it's a slightly different thing. It's on a hexagonal lattice. Right? So the hexagonal lattice, again, just means, yeah, so this is, right? So that means it's, well, I'm not sure which one. I think that's out of the shirt, and that's in, and then into the shirt, right? So you have 6 possible things you can do at each point. And so you put it on a hexagonal lattice, which is an awesome lattice, and we'll come back, hexagons are the best. We'll come back to that. And I let it run. It's pretty funny. And then and I said they have these other things. They have a symmetry one, which is, this is the sum of the number of left and right ones, right? Left and right moves. So you want that to be as close to 0 as possible. And then this is this winding thing, which means if you go clockwise, you get a +1, or anti-clockwise, you get a -1. So you'd want them to, this little bit to be 0 as much as possible, right? To balance itself out. So I think, so the Windsor, so let me try the Windsor. This is very funny. So it's this one, right? So it's going to be, so you go over left, and I guess into the shirt, and then center, right, you're coming out, and then you go around to the right. Yeah, that's the one I always messed up, right? So you make this little structure here. So we're here, and then out with the left. Very good. Yes, it's really ridiculous. And then in through the center, and then out through the right. Did I get that right? Did I skip something? So I've left, in, and then I need to do the right coming out, and then left coming in, and it's got a nice structure, right? So this is good. Windsor, which is a, right? There you go, and you get, it's a good solid, did I get it wrong? What did I do? That's right. So it's a good solid, it has heft to it, right? Which is the thing, whereas the, look at this Weasley little thing, that 4-in-hand thing is, so it's left in, and then this is just, it's awful. And then this is a right, and then just left around. This is just so sad. And then this is your decrepit lawyer tie. And it's just this sad little, see, so sad. And it has what's the symmetry on that one? So that's interesting. Oh, the Windsor has a slight symmetry bias here. And this one does too, but it has excellent, this ridiculous winding balance thing is good. But humans had figured these out, and then the suggestion is, maybe these ones aren't too bad. This one here is just a rock star, but no, right, it's got some good stuff going on here, but not discovered. I should tie that, but I think I should keep going. Should we just tie ties? Does anyone want to tie a tie? Anyway, great moments in random walks. That was pretty good. That's true, I should do that one. So what is this? Left, right, center. So around the back, center, and then left, right, center. Oh, look at that, very nice. Yeah. It's just like building a house, basically, right? That's just like, just reinforcing one thing. It's like, do it again. Anyway, pretty great. So now and then you get these papers in Nature like this that I think it's pretty good. Okay, good. Yes. Yeah, but I remember the senior boy saying, no, not like, that's not right. You tie it like this. Okay. Okay. So first return, what's the probability that a random walker comes back? So this is a bit different, some of the things we've talked about, but what's the probability they come back after t time steps? It will have to be an even number of time steps. And we know that what's the probability they come back, even if they've come back before, that fits into this Gaussian distribution, right? They could come back a whole bunch of times, and we could say, after 100 time steps, what's the probability they come back? That fits into the Gaussian distribution, so we already have that. But what's the probability that they come back for the first time? So this has a little bit of sneaky math involved. And then there's this question, will they always return to the origin? And what about higher dimensions, right? So if we're in 2 dimensions, so you can step this way with a quarter of a chance, this way, and then let it go. So one thing you can see about that, right? So if you step out to here, now you've got 3/4 of a chance of going somewhere else, right? And only a quarter of a chance coming back to here. So the escape probability starts to kind of go up, right? And if you have 3 dimensions, suddenly you step away from this thing and you've got how many? 7, right? So you can see if you're in 17 dimensions, which I choose very carefully, then you're going to disappear, right? Okay. And that sounds weird, but actually places that have that many dimensions are networks, right? So networks are weird structures, and if you think about a network and the number of friends that a node has, that's its local dimension. Think of it like its local dimension. Right? So some network where you have a hub that has 10,000 connections, that's like a really high dimensional space, and it behaves, if you have a process running on it, locally it's going to be sort of operating in these different dimensions, roughly. Networks are cool. We'll get to networks. Okay, so reasons for caring. Well, I'll claim. So we're going to find a power law size distribution, which was sort of the game here. Physical structures, such as ties, come from random walks, but lots of things. And there's a piece here about scaling relations. So we've talked a lot about scaling, but I don't think I've said anything about this, where you can have different exponents related to a system that connect to each other very simply. And usually it's just algebraic, like alpha plus beta equals 3 or something like that. Okay. But that's a beautiful thing too. Okay, random walks. Okay, so let's look at this one. So we've got a 1D random walk. We're going to have 20 steps. This is one that starts at 0, ends at -4. It's just an example one. So basic things, we're worried about this first return. So a return to the origin, you know, and this is work that really was done in the 20s by Georg Polya, who's very famous. We'll talk about him again. But it took 20, 30 years after that to sort all that. So, so first of all, we know that it has to be an even number of steps, all right? We have a first return, well, we have returns happening at 8, 10, 14, and that's what happens here, but the first return is here. And if you like, then we actually really have a sequence of, if we just imagine, okay, let's start again. Now we have a first return after 2 time steps, first return after 4 time steps, so it's a sequence of. Okay. So we're going to write this. This is probably the first return at 2n. And so it's a counting problem, right? Combinatorics, if you like combinatorics or statistical mechanics or anything, you know, but it is counting. It's all just super counting. Very careful counting. We like counting. And we're going to turn it into an easier problem because it's an odd one. You realize you somehow want to exclude. Somehow we need to figure out how to exclude. Right, if we were thinking about which ones return after 10 time steps the first time, we can't use this walk, right? Because this has already come back. So how do we exclude that one in a simple way? All right, so here's one that first returns after 16 time steps, just an example one. And what has to be true is that, you know, and we can flip it if it went to -1 first, right? So there's sort of no loss there. But if it goes this way, then at time 15, we know it has to come back. Right, it has to be at step 1 here, right? It has to be 1 step away here, and then it has to take that chance of going back to the origin. All right, so now if we do that, we have something. So it has to stay, and it has to stay above this red line, right? So it can hit it, but now we can think about a walk that does actually return to the origin, and we have calculations for that, kind of. And what we'll do is we'll sort of just split off this bit here and split off this bit here and try to think about counting these types of walks. Right, so it's again a counting problem. We're going to transform it into something else that's easier to count, or find a piece of it, or see it in a way that makes it easier. Okay, so yeah, well now we can have walks. It's not quite what we had before. We can have walks that return to 1. They can't go below it. So probably the first return after 2n time steps is the same as having a walk that's at least 1 between 1 and 2n minus 1, right? So between here and here. It has to be at least 1. And it has to be that it starts at 1 and ends at 1. Okay. We get a couple of pieces here. There's 2 because the walk could have gone underneath. It could have gone on the negative side. And there's a 50-50 chance at the end that we get the right thing here. So they're just some little corrections. And that's written here, right? Okay, and the 2's account for those pieces. Okay, so we're transforming this, right? We're interested in the ones that first return, in this example, after 16, but we could also equally take ones that start at 1, end at 1, and they over this smaller time scale of 14 time steps, actually. How do we do that? Okay, we're going to count things, and we'll get back to probably at the end. So we have this piece that you're going to figure out, which is the number of walks that start at I, end at J, after 2 time steps. So that's a base piece that once you figured it out, we'll use it again and again. And first of all, we're going to think about all the paths that start at x equals 1 and end at x equals 1 after 2n minus 2 time steps. So we had 16 before, so this would be 14, right? It's just that we're chopping off the ends. So what we're going to do is this. So the idea is we want to calculate the number of walks that actually go to 0. If we can compute that part, right, the ones that we're trying to exclude, if we can count that some way, then we can subtract them off from all of the walks that start at 1 and end at 1. So we know how to count all of the walks that start at end at 1 and end at 1. That's from the Gaussian thing that we had. It's just a binomial. If we can figure out the ones that kind of errors, if you like, or do the thing we don't want them to do. If they go to 0, then we'll get rid of them. So we call them excluded walks, and it's a method of images which is used in lots of different systems. But I guess I should have the right picture here. Yeah. I was going to go back, but let's not do that. Okay. I'll stand on something. So, okay, so let's look at this one in black up here, right? So it starts at 1, right? This is the 16 time steps, ends at 1 here. That's all good, that's what we wanted. But it does something wrong, actually, right? It hits 0 here. So the idea is, if we take where it hits 0, and take all this first hit 0, and we take all of the walk before it and flip it around 0, then we make this blue one. You see that idea? Okay, so this is a sneaky thing. We're going to take the part that gets to 0, flip that part, and we make a new walk, the walk in blue. And so this is another example. It hits 0 here. It actually goes below it, hits 0 again. Both of these walks in black, they hit 1 here, and they hit 1 here. And that's all we want them to do. And now we're finding the ones. We're finding a way of figuring out which ones actually go below 0. So again, this blue one is a flip of the black one from everywhere before it first hits the origin. So these blue ones will exactly equate to the ones that do this bad thing, right, that hit the origin. So that's the idea. You can imagine anything that starts at -1, because it has to start at -1, ends at 1. At some point, it has to cross the origin. And when it does that, you flip the first part up, and you'll make one of these bad walks, or excluded walks. Right? So we can turn it around the other way. Take any walk that starts at -1, ends at 1, over this time scale, flip the part that is below, and we'll make a walk that we don't want. We'll make a walk that starts at 1, ends at 1, and it has to hit the 0 at some point. Yes?
But you don't flip the second part.
Right.
It crosses multiple times.
Right. And you want to think about that and make sure that it's a one-to-one mapping. But this is, this is exactly the kind of walk that will get to there. And right, it ends at -1, ends at 1. And it will make one that starts at +1 and ends at 1. It'll get you one of these excluded ones. Because they have to hit 0 at some point, you're going to calculate, you're going to get all of them. So there's a one-to-one correspondence between those things. Now, these blue ones, all we're saying for them is they just start at -1 and end at 1. We don't have any restrictions on them. And then that's one of our easy to calculate walks, right? So that's just this n number. So we'll get this n thing. We'll get back to that. So there's a unique match between them. And I have 9 more minutes. Okay. Okay. Super tired last week. Okay. I think I was tense about a race. Anyway, so, and then, okay, so this is just saying what I've tried to say. Yeah. So, so the number of t-step paths that start at 1, end at 1, but hit the origin at least once equals the number that start at -1 and end at 1 over that same time scale. This is the number of them, right? So we can write that down, and this is what we get. So the number of first return after 2n time steps is equal to the number that start at 1, end at 1, and take 2n minus 2 time steps to do it, right? They're the ones in black. And so this number includes ones that hit 0, but we're going to get rid of them because we'll get rid of the number of them because we'll say, take out all of the ones that start at -1 and end at 1. Wow. It is someone from my iPhone. That's so weird. I wish it wouldn't do that. Gosh, all right, I'm very sorry. No idea why it does it. Okay, all right. Is there, like, your phone just like, it takes over the phone? Because no one uses a phone as a phone, right? And yet we still have this thing, like an iPhone at least, it's just like, if someone calls you, it's like, this is just an emergency, and it's like, blacks out the whole screen, and you can't like get rid of it. But I was hearing this other thing that, this is millennials, right, don't like doorbells, apparently, because you just text, right? I mean, you know where everyone is. I mean, what would you use a doorbell? And like a doorbell is a real violation of self. Yeah, okay. You're like attacking, yelling at the person by just. But phones certainly slipped into that. Like, why would you talk to someone on the phone? Okay, I'm totally with the millennials on that actually. Anyway, so, okay, so right. What am I? I'm Gen X. Yeah, no one cares about Gen X. We did invent things. Okay, so there's this, and the boomers. Wow. Terrible. Okay, so we have, yeah, this, good, right? And this is just actually kind of a Gaussian sort of a thing. I mean, in the limit, minus a Gaussian sort of thing. But it's a binomial minus a binomial. So this is an algebra thing, right? We're going to have a factorial over a couple of factorials, a factorial over a couple of factorials. You have to smoosh them together, which is, like combining fractions, basically. And then play around with a little bit. And the big piece that's not, in these slides, but I'll tell you how to use it, is that you will, well, all right, first of all, you're going to find this. You're going to get to this. So the number of first return is going to scale in this way. There's a big 2 to the power of blobs up the top, but that root 2 pi will, root 2 pi, this is a beautiful thing. Root 2 pi will appear here. End of the 3 halves will appear here. And so if we turn this back into, if we say t is 2n, and we have to think about the number of possible paths, right? We've had t is 2n time steps. That's how many there are, right? So it grows enormously, exponentially, right? 2 to the 2n, right? You've got 2 possible paths after 1 step, 4, 8, 16, So we're going to divide by that. And if you do that and you do that carefully, you will end up with this. I don't know how I'll ever get this to work. That's just dividing through. We're going to clean it up. This is 2 to the 2n. It's going to cancel here, cancel here. So there's 2 to the minus 3 halves, so we can stick it with this character. So that's what that is. Come on. Ah, nope. All right, so just snap this 2 to the minus 3 halves down here, and then we get basically proportional to the minus 3 halves. So this is a power decay, right? So the probability that you come back to the origin after t time steps, so we ignore the odd even thing. Basically, decays is 2 to the minus 3 halves. This the weird thing about this is, right, is that this expires between 1 and 2. So t to the minus 1, you integrate that, log, it's not normalizable. T to the minus 3 halves, you normalize it. If you try to compute the mean of this thing, get infinite. So the mean, variance, all the higher order statistics are infinite. So probably this character returns 1. The expected time to do so is infinity. So this is a really kind of bad power law situation, right? Most of the things you sample out of this sort of distribution will be bigger, right? Because on average you get infinite sized things. So if we think of the sizes here as the time it takes to get back to square 1, then sure, you'll get some really small ones. You'll get a bunch of 2s, right? Half the time it comes back like that. You'll get a lot of little 2s and so on. But you'll get some monsters. As you keep sampling from this, bigger and bigger things will happen. And the analogy, right, for floods and earthquakes and these things, right, is that you will get bigger and bigger ones, but somewhat rapidly, because this is this t to the minus 3 halves is a slow decay, right? It's a heavy tail. It's got a lot of room out in the tail. Okay. Excitement? So these sorts of distributions never really appear in, I don't know, a lot of areas, right? I mean, statistics, they don't like to talk about it. Physicists have them all over the place. They're just because reality. So we're kind of, we're pro-reality in this class. So, all right, so that's cool. And I think we might be, so you guys will figure this out. Is this plan? Okay, so we've got these things. These are the words. Okay, so it's normalizable, right? So you can integrate this thing and set, if you've got some constant or whatever at the front, you can set that so that you get integral of p of t is 1, or the sum of p of 2n is 1. So that's good. That means it always comes back, but the mean, variance, all these things are infinite. So we have to expect right? So never play against wealthy people who can flip coins, right? So it's not good. I mean, there is, in blackjack or whatever, you can If you just keep doubling your bet, right, in principle, you will win. But that will go bad one day, and you will have nothing. So, so count cards. So, actually, when I was at MIT, the card counting kids were there then. I think they made a movie out of this. Yeah, it was a thing. They train each other up and go to Vegas and, yeah. So now, like every TV show has, like, if there's a Vegas thing, there's someone who counts cards and the people, they get put in, they get tortured or something, something like that. It was pretty good. So higher dimensions, you ask, what happens? So in d = 2, you actually always come back. Again, it's infinite. It's still a disaster. You'll never see them again on average, but they will come back. So if you wait at the pub, you will find them again, but it will take an infinite amount of time. So you should walk away, but it's weird. But at higher dimensions, there's more ways to escape, and indeed they do escape, right? And this is also, this is Polya figured this stuff out. Here is the insanity associated with this. Right, so here are random walks, right? 3-dimensional random walks, good fun things. There's some structure to them, which is weird. Let me show you this. See, we're not going to do this nonsense, right? But this is...
Have you seen those ant colonies that they've poured molten aluminum into and then they dig out the aluminum?
Oh, right. Yeah. And then you have the thing. Well, and then you can measure the shapes and all these things, right? So actually it's hard for trees because no one's really done this well for trees. We have this idea of tree bots, things that run around a tree and you get the whole shape for a big tree. I will say that people do this with animals, actually. Pour some stuff into the animal and remove the animal, and you have the blood network. Enterprising. Thank you, science. Okay, so so this is from. Wolfram is insane. He's a disaster. But this is from their page. This is Look at this nonsense. So it's a bit of hard work to actually figure out the details, but. Gamma functions will become your friend, but there it is, gamma functions and madness. So it's less than 1 is really all you need to know. But yeah, wow. So you can go kind of Barney Bananas with that if you want. Polya, we'll talk about Polya, but you might want to look him up. Lots of interesting things. What we'll come to in the next thing is urn models, which just doesn't have a good modern feel to it. But urn models, it's just you have a container and it has balls inside it of different colors, and you pull out a ball and you have different rules, like different kinds of games. So maybe you pull out a red ball, and if you do that, you put it back in, but you put another red ball back in, and then keep doing it. So it's a weird sampling game where you grow the number of balls, but there's sort of a rich gets richer phenomenon potentially, which is going to be a big deal for us. But Polya is famous for that. It's famous for lots of things. Famous for being very smart and telling other people how to be, heuristic kind of ways to think about things. I did have this other thing here. Did I lose it? Sorry. I guess I lost it. Oh, yeah. So maybe this one. Yeah. Faster. Run. Can you see that? That's very hard to see. But this is exactly this. Right. So it's kind of nice because it traces out the random walks. So it's exactly the first video I showed you and my little sketch, but yeah, it's very satisfying. Yeah, I mean, the Romans made these things, right? I mean, that's the quincunx, which is a ridiculous word, but people have thought about these things for a long time. Okay. So I think that's a good thing. So let me tell you about just last piece here. Yeah, last little slide, sorry. So on finite spaces, so this is an infinite thing, right? They can keep going. On a finite space, if you had this random walk and you could only go to the edges, right? So if you go to the edge, you bounce back, there's a little thing. Or if you're on a loop, something like that, and we make this a loop. Oh, so we do the normal math thing, which is if I walked to here and then stepped here, I would appear over there, right? Wrap around boundary conditions. Totally normal. If you do that with a square, you get a donut, right? Okay. So we've done lots of math on donuts for no apparent reason. Anyway, so that would mean if you look at in a long time, the probability that anyone is this random walkers, they'd all be evenly distributed. So this diffusion on a small space or a finite space gives you even distribution. However, very interesting. So that's what this is all about. We talk about invariant density, and you get interesting invariant densities with other dynamical systems where they're chaotic and you get strange attractors, and that's the story there. But here's a basic thing: diffusion on networks. What happens is eventually what you see is if you're watching these little people walking around the network, you'd see that each edge had the same number of people on it, but the nodes would have the number of people walking through a node would be proportional to the degree of the node, the number of friends the node has. So the diffusion is actually an edge space where it's even. I know I've talked for too long. It's even on the edges, but it piles up at the nodes. And actually, Google basically, that was the Google algorithm, was random walkers on a web and used that kind of process. So also important. Google has been important and random walks. Okay, thank you team. Office hours, I will probably be a little bit late, but I'll try to get there as quickly as possible. I will stop talking. Thank you.